6-2. All right, this is going to be a little easier, like I said, than yesterday. Yesterday's stuff was pretty hard. We're going to do vectors and their dot products. Vectors and dot products. All right. So, so far, we have had some vector operations already that have been quite easy, right? And vector dot products are going to be pretty easy too. So we have operations for vectors. And they've been very basic, like, you know, you add two vectors, you get a vector. You have a scalar times a vector, you just distribute that number in, that constant. And so today what we're going to do is we're going to learn the dot product. Now, I was looking in the book, and I was thinking about this last night when I was going to bed, because I was thinking, what am I teaching tomorrow? And I was thinking about dot product and how to explain it to you. And I was thinking, well, what is a dot product? What even is it, like, picture-wise? I don't even know, and I'll tell you why. And I found out this is why. I went to your book, and it says right here, the dot product results in a vector perpendicular to the plane of the two vectors being multiplied, which takes us into a third dimension and outside the scope of this chapter. That's why. It's beyond us, okay? So we're not going to, like, get through the stuff of, oh, why is it and what is it, and we're just going to do it. And that's sometimes we do that. So that later on, if you do take a higher level vector class, which I never did, I didn't take that. What? You might. I don't know. You could take vectors in college or something. I did not. So, all right. So here's what the dot product is. The dot product is to, excuse me, take two vectors and multiply them together. But you're not just going to take A times A and B times B. Remember when you did matrix multiplication? You had to go across the row and down. It wasn't just this times this, that times that. It was like, whoa, that's different. This is going to be kind of that same thing, like it's different. So let's say you have vector u, and vector u is equal to u1, u2, u2. I saw them in concert. They were pretty good. And then vector v is v1 and v2. Now, some people don't like using u's and v's because they look too much alike. The book loves to use u's and v's for vectors. So to find the dot product of u and v, we write this. U dot v. Okay, we don't really say times. It's not u times v. It's called the dot product or outer product or vector product, cross product, whatever you want to call it. U dot v is equal to, this is what you do. You take u1 times v1 plus u2 times v2. And that's it. Now notice what you get. What do you get? Do you get a vector? No. You get a number. Isn't that weird? You take the dot product of two vectors and you get a real number from it. And that's it. Okay, make sure you know that. We're going to do some easy examples, and then we're going to we're going to do we're going to apply this to one thing, just one thing. Okay, by the way, your operations, you have some properties for operations. Some of them are kind of duh properties. So there are 5 of them. And the book goes through the proof of 1 and 2, and that's it. So if you want to see the other proofs, you might be able to on your own. All right, so u dot v is the same thing as v dot u. So they are commutative. So dot product is commutative in vector world. U dot v equals v dot u. Okay? Number 2. 0 times any vector. What do you think that is? 0. 0. 0. So there's our 0 property. That works. Property number 3 says if you take a vector u dot vector v plus vector w, the distributive property works here. Oh, you need some rest this weekend. So you would do u dot v plus u dot w. Okay, and you're like, yeah, these properties are great, yay. These properties did not work. They didn't work in matrix world, remember? Remember matrix A times B was not B times A? So it's kind of like cool, like, oh, vectors, it does work, because we've seen places where it hasn't worked. All right, number 4, here's one that's kind of an interesting one. If you take V dot itself, V dot V, this is going to equal the magnitude of vector V squared. Yeah, you could prove that one pretty easily. Do you want to prove that one?
No.
No? Maybe on a quiz.
No, then do it.
Oh, now you want it. All right, and then C, some constant times U dot V is equal to C times U dot V or U times CV. Okay, so you can take that constant. You're not going to distribute it to both, but one of them can get the constant. I would probably do U dot V first and then multiply by the constant at the end. That's what I would do. All right, you ready to do some problems now?
Wait.
Yeah?
Is that actually going to be on a quiz?
I don't know. Maybe it's a good bonus question to prove that.
Yeah, those are the ones I skipped.
Perfect. All right, so let's do some examples. Number 1. All right, let's say here that vector u is equal to -1, 3. Vector v is the vector 1, -2. And w is given to us as 2, -4. Okay. Okay, let's just start by finding the dot product. Let's do the dot product of what? Let's do u and w. Let's do u dot w. Okay? So you're going to need to know this. It's kind of like a formula. You need to know this for your quiz on Monday. I'll ask you for the dot product of something. I won't have the formula on there for you. So you need to know that you're going to take -1 times 2. So u dot w would be these two vectors here. So -1 times 2 plus 3 times -4. And you'll have your calculator. It's fine. Ooh, you could write a program for that. All right, so you get -2 minus 12. So the answer is -14. Did I do it right? Sometimes I mess up on the math, the number part. Okay, let's do another one. Let's do B. Suppose that we have u dot 2 v. All right, a couple ways to do this. You could do u dot v and then multiply by 2 at the end, or you can go 2 times just v and then dot u. And I think I'll do it that way. So u is -1, 3 dot 2 times vector v would be 2, -4. Hey, we already did this. That's funny, huh? Isn't that funny? No? Isn't that 2, -4 the same thing as w right there? Yeah, so the answer is going to be -14 again. Interesting. Okay, do I have any more of those? Yeah, I did that one, Pretty good. All right, so you get that. You're pretty good on that. All right, let's do part B now. Last part, and then I'll answer all your questions from last night's stuff. Okay, we're going to find the angle between two vectors. Angle between two vectors. Okay? So suppose that you have a vector. We'll call it vector v. And then suppose that you have this vector over here, and we'll call that vector u. And let's say we want to find the angle between these vectors. We call that theta. All right, and then if you have this vector over here, they call that vector, the vector's called a couple of different things, but they call it vector v minus vector u. Okay? That comes from the parallelogram law. If u is going in the opposite direction and then you had v, that would be the vector v minus u. All right, so here's the formula. There is a proof. I'm not going to go through it with you, but it actually uses the law of cosines. And it's like a doable proof, but we just don't have time for it. So to find out what theta is, what you're going to do is this. Cosine of theta equals u dot v over the magnitude of u times the magnitude of v. Okay, do you remember what the law of cosines was? It was like cosine of a was b squared plus c squared minus a squared all over 2bc, right? That's where all this stuff right here is coming from, but it's just in vectors, and it's actually a lot nicer. It's like cleaner in a way. All right, so go ahead, put a little thing around this too. And now we're going to just do one. And they're pretty easy. You don't have to find this other side over here. Because you know, when you have this angle right here, you're supposed to have side, side, side and use law of cosines. I don't need that third side. All I need is u, v, and the magnitudes of u and v. Okay? So let's do one. Here we go. Number 2? Number 2. And this is the last one of the day. This is going to be an easy lesson for your weekend. We're going to find the angle between vector u, which is 4, 3, and vector v, which is 3, 5. All right, and you're going to need your calculator for this because we'll end up taking the cosine inverse. It's warming up, isn't it? Yep. Okay, so let me draw a picture of this so that you know what's going on. Okay, so here we go. We have 1, 2, 3, 4, 5, 2, 3, 4, 5. So vector u is 4, 3. 4, 3, so there's vector u. And then vector v is 3, 5. It's up here. And we are trying to find this angle between them. Okay? Now, you can do this a variety of ways, you know. You could do this by finding the distance of that vector, the length of that vector, the distance between those 2 points, and then the distance here, and you could use law of cosines. You see that? You have all that. You could totally do that. But let's not. Let's use this better formula up here using vectors. So we're going to do cosine of theta is equal to u dot v. Can you do u dot v in your head? I have no problem if you can do u dot v in your head. U dot v is to do 4, 3 dot 3, 5. So you're going to go 4 times 3 is 12, plus 3 times 5 is 15. So that would give you 27 up top. Okay? And then you have to find the magnitude of u. The magnitude of u is easy. What's the magnitude of u? Here's u. It's a 3, 4. 3, 4, 5. Okay? So the magnitude of u is 5. V, not so nice. It's not the 3, 5, 4, unfortunately. So the magnitude of v would be the square root of 9 plus 25. So rad 34. Okay, now we're ready. I love this because I was thinking about this last night. Like, you don't have to find that third side. You don't have to use the distance between those 2 points and find it and do law of cosine. So you use vectors, it's so much better. All right, so what I would probably do is I would go 27 divided by parentheses 5 rad 34. And I'd hit enter. And then I would take the cosine inverse of my answer, and I would get that theta equals 22.2 degrees. And then I go and I look at my picture, my drawing, and I say, does that make sense? Do you think that's about 22 degrees in there? Sure. It could be, you know. I could use law of cosines to check it, but I'm not going to.